So let's just pick up the thread from where we left off at the end of the last lecture. So just to remind you of where we were, so we were discussing
Recording
the
stopped.
out-of-time ordered correlator, the OTOC or OTOC. And what we argued
Recording
was that,
in progress.
okay, right. And so what we argued was that for a quantum system, the quantity to calculate which is equivalent to what you would calculate for a classical system in order to look at the divergence of trajectories and extract a Lyapunov exponent, the corresponding quantity for a quantum system is the expectation value of this particular object, which is the square of the commutator between two operators. And one of these operators is evolved in time, and the other one is just the operator time t equal to 0. So you look at quantities like this, and in the simplest case, of course, if you have a classical equivalent of the model, then and also a classical equivalent with very few degrees of freedom, for instance, with just 1 degree of freedom like the kicked rotor, then these quantities can very conveniently be taken as the canonically conjugate variables of that system with 1 degree of freedom. So in the case of the kicked rotor, these were basically the position and the momentum. And so one can calculate this. Now doing the calculation for, so performing this calculation even for a system with just 1 degree of freedom analytically is difficult, is hard, and so then one has to resort to numerics. And of course, if you're going to do this numerically, then you have to somehow make the calculation finite sized or finite dimensional, because the quantum mechanical system, even though it has 1 degree of freedom, has an infinite dimensional Hilbert space. And so there's one truncation that takes place, which is basically restricting the dimension of the Hilbert space to something finite. But then there's another thing which is very important, and which is really what distinguishes the quantum system from the classical system, which is that for the quantum system there is an h bar, a Planck's constant, and what it does operationally is that, again, we're talking in the context of the kicked rotor. So for the kicked rotor, whose canonically conjugate variables are the momentum p hat and the angular position x hat. So what we know is that p hat as an operator has eigenvalues which are of the form an integer times h bar. Whereas if you looked at the corresponding classical problem, and if you looked at the classical momentum, that doesn't have any discreteness. So that's a continuous variable. Whereas here the allowed values of p hat are discrete, and the discreteness of p hat is given by h bar. So the quantumness of the problem is reflected in the existence of a non-zero h bar. And as you take h bar to 0, then of course you start getting to the classical limit. If you really wanted to go to the complete classical limit in which there is also no restriction, so like I told you in the last lecture, restricting the Hilbert space dimension is equivalent to classically in some sense restricting the energy that the kicked rotor can have. And so if you really wanted to go to the completely unrestricted classical problem from the quantum problem, you'd have to take h bar to 0, and you would have to take the Hilbert space dimension to infinity. Now what we also saw was that one of the consequences of having a non-zero h bar is the existence of this time scale called the Ehrenfest time. And the Ehrenfest time is basically the time scale over which a wave packet that you have created in order to mimic a classical state or a classical phase space point. So this is the time scale over which this wave packet spreads because of the corresponding classical chaotic dynamics. So it's a time scale over which this wave packet spreads to having a width which is of order 1. And so the best you can do in terms of the width of the initial wave packet is something which is of order h bar. And so therefore the time scale over which this initial wave packet with width of order h bar spreads to having a width of order 1 because of the classical chaotic dynamics which has a Lyapunov exponent is the Ehrenfest time scale. And what we saw was that Ehrenfest time scale is basically of the order of 1 over the Lyapunov exponent times mod of log h bar. And so in the limit that h bar goes to 0, this time scale goes to infinity. But otherwise, if you have a finite h bar, then this is a finite time scale. And that is something that you can see in this plot here, like I showed you again in the last lecture, that as you increase the value of h bar, the time scale over which the spreading happens, or the Ehrenfest time, decreases. So for the smallest value of h bar, you have the largest Ehrenfest time, and the Ehrenfest time here is the time scale after which this object here, which is really the Lyapunov exponent that's calculated from the OTOC, the time scale after which the Lyapunov exponent ceases to be a constant. It actually acquires a time dependence, which happens because the OTOC has now saturated. So this is the Ehrenfest time here, and you can see that Ehrenfest time is actually decreasing as h bar is increasing, as you would expect from this formula. Okay, and also just to remind you of what the quantum kicked rotor is, the Hamiltonian for the quantum kicked rotor is given there. And just to make contact with the kinds of things that Arnav has been telling you, this is an example of a flow case system, like I told you the last time. In fact, it's a much simpler kind of flow case system compared to the ones that he's been talking about, because this has this 1 degree of freedom. And also the fact that you have these delta functions here means that you can write down the flow K unitary in a rather simple way. I mean, so writing down the flow K unitary for this model is not complicated. Unlike, for instance, the sort of spin models and other models that Arnav has already talked about and will talk about, for which even constructing the flow K unitary is difficult, but here it's not. Okay. So this is where we were at the end of the last lecture.
So in the classical case, nonlinear dynamics, they make a distinction between this finite time Lyapunov exponent and this infinite time. Sometimes they take the limit t going to.
Right.
So is it because of the existence of this Ehrenfest theorem that it doesn't make sense to look at the infinite time?
Are you talking? Yeah, here for the quantum system, yes. So this is all right. Exactly. Okay, fine. So let me also just mention something else which is not directly related to anything else that I have to say, but is nevertheless perhaps interesting, and also my own vested interest in this is that it's something which I've done with my students. So let me just show you something a little quaint about the OTOC and the kicked rotor. So it turns out that one can also write down a non-Hermitian version of the kicked rotor. Now, right at the outset, you might say, so by which I mean that one can write down a Hamiltonian, which is not a Hermitian matrix or a Hermitian operator. And you might say, well, what does that mean? In quantum mechanics, we've always learned that the Hamiltonian has to be a Hermitian operator, and that has to do with the fact that its eigenvalues, which are the values of allowed energy, have to be real. So if you write down something that's non-Hermitian, then in principle, its eigenvalues are not real, are complex. So what does that mean? I mean, so you can write down something like this. Yes, mathematically it might be interesting, but what does it have to do with anything that's real quantum mechanically? So it turns out that non-Hermitian Hamiltonians are also perfectly interesting in their own right, even from the point of view of applying them to physical systems. And so one example of actually using non-Hermitian Hamiltonians to look at physical systems is when your physical system is not an isolated system, right? So if it's an example of what's called an open quantum system. And in my last lecture, I'll tell you a little bit about open quantum systems, although not from the point of view of non-Hermitian Hamiltonians. All the same, the main point is that imagine that you have an open quantum system. So an open quantum system is a system in which the degrees of freedom specifying that particular quantum system are not the only ones. There are other degrees of freedom that these are interacting with, which in some sense provide a bath for this quantum system to exist. So imagine that you have a system like that. Also imagine that the bath that the system is in contact with can supply particles to the system, the quantum system of interest, and also take particles out of it. Okay. So think of the quantum system of interest as some system of particles, and the bath also as being some, among other things, another system of particles, which can supply particles to the quantum system or also extract particles from the system. So then what's going to happen is that the particle number of the quantum system is not going to be conserved. And this is, again, something which you're very familiar with in statistical mechanics, that in statistical mechanics, when you have a system in thermal equilibrium with a bath that can supply particles to it or take particles away from it, then of course the particle number of the system under consideration is not something which is constant, it has fluctuations. And thermal equilibrium is actually described by a chemical potential rather than a fixed particle number. So again, think along similar lines here, except that now the system doesn't even have to be in equilibrium, it's just in contact with the heat path. And so particles can escape or come in, and so there's no conservation of particle number. And so if you think of, well, if you think of this dynamically in terms of what's happening to the system of interest, then one way of looking at this loss of particles is basically to think of any wave function in this system, right, describing the particles as not having a constant normalization. So if you think of, just say, a single particle quantum mechanics, and you think of the wave function of a single particle, the fact that the wave function is always normalized, right, and that normalization does not change under the action of a Hamiltonian if you have an isolated quantum system, simply tells you that there is you can find the particle anywhere within the domain of the system with probability 1, that there's no way in which the particle can escape the domain in which this quantum system is defined, because there is nothing else. But now, if you have the system in contact with the bath and you don't have a conservation of particle number, then in some sense heuristically you can think of that situation as being like one in which your wave functions don't have a constant normalization, that the normalization can actually change as a function of time. And so you know that one way in which you can actually think of a normalization changing as a function of time. So I mean, just crudely speaking, if you have, for instance, some initial quantum state psi 0 for a closed quantum system, and you look at its evolution as a function of time, then this is the way it evolves. And the reason that the normalization is preserved is because of the fact that this is a unitary operator, and the fact that this is a unitary operator goes back to the Hamiltonian being a Hermitian operator. And so now, if you, for whatever reason, you don't want the normalization to be preserved, then one way in which that can happen is if the Hamiltonian in question is actually not a Hermitian operator. So this is a way in which you can think of non-Hermitian.
One quick question. So of course, if you have these non-Hermitian thing, ultimately at late time there will be nothing, right? Because you flow to
right. Okay. Yeah. So well. Okay. So that when you say there will be nothing, there's either going to be nothing or there's going to be a lot, right?
Exactly.
So that depends on whether the imaginary part of the eigenvalue of the Hamiltonian is positive or negative.
Yeah.
Okay.
But both of them are sort of unphysical.
Right. So what you typically do when you look at open quantum systems in the language of non-Hermitian Hamiltonians is that you're really okay. So you either look at the system for only some fixed duration of time. So that's one way of doing it. The other way of doing it is that you, even if you want to look at some steady state that you have achieved, then you really have to think of situations in which you both have positive and negative imaginary parts of the energy. And then you can get, something that's oscillatory. Okay, not oscillatory, but well, okay, I have to be a little careful in choosing my words. Okay, how about we talk about this offline, right?
I'm a bit confused about that, but I'd like to
Yeah,
understand.
sure. Okay, so anyway, but this is just to tell you about why you might even be interested in non-Hermitian Hamiltonians. The particular non-Hermitian version of the kicked rotor that I showed you here is really more something that's mathematically interesting than a model which applies to a real physical system. But you can see that you can make the kicked rotor non-Hermitian in many different ways. I mean, so for this particular system, I have chosen to make it non-Hermitian by introducing this term I lambda sine theta. So if lambda is equal to 0, then you get back the usual kicked rotor. And for the usual kicked rotor, of course, the k cosine theta term is like a potential that the rotor sees, which is switched on stroboscopically. Now what we have is, we actually have a potential which is not a real potential, but a complex potential. So this is one way of making the Hamiltonian non-Hermitian. You could have also, for instance, introduced some non-hermiticity here in the kinetic term instead of in the potential term. It just turns out that for what we were specifically interested in this study, it was just useful to do it in the potential term. So this is a non-Hermitian Hamiltonian. And so you can actually go ahead and, but it's still a Floquet Hamiltonian, by the way. Just because it's non-Hermitian doesn't mean it's not Floquet, because it's still periodic with a period of this time scale t here. And so one can, in principle, again, do the same kind of calculations for this non-Hermitian Hamiltonian that were done for the Hermitian Hamiltonian. In particular, ask what is happening stroboscopically at instants of time, which are integer multiples of this t. How are things evolving at those instants of time? And in particular, one can also calculate the out-of-time ordered correlator for this non-Hermitian Hamiltonian. The one thing to be careful about, though, is that because of the fact that the normalization is not preserved, the out-of-time ordered correlator in general has an exponential increase with time. So if you just contrast this to what you see here, so for the Hermitian case, you actually see an exponential increase followed by this plateauing due to the Ehrenfest time, the existence of the Ehrenfest time. Here what you see is, if you just calculate the OTOC, you don't really see, this is on a log scale, you don't, this is on a log scale, you don't really see the plateauing, you just see this continuous exponential increase. But that doesn't mean that there is no Ehrenfest time, because this exponential increase is really happening because the normalization itself is changing as a function of time, right? And so what you have to do is you actually have to normalize the OTOC by the normalization. You have to divide it by the normalization. And when you do that, you actually see this saturation. So that is the C tilde of t, which is the bare OTOC, then divided by the normalization. And once again, you see a saturation of t. You see a smaller region where you have an exponential increase from which you can extract a Lyapunov exponent. And indeed, that's what we've done here. So by the way, this is really very bad notation on my part. The lambda in this case is not the Lyapunov exponent. It's actually this quantity here. The Lyapunov exponent, on the other hand, is LE. And so there is a certain dependence of LE on lambda. And so one of the things that you can see here, which you don't see in the Hermitian kicked rotor, is that as opposed to for the Hermitian kicked rotor, where when you calculate the Lyapunov exponent as a function of the only parameter in the system, which is the kicking strength, and you see that there's a monotonic increase of the Lyapunov exponent with the kicking strength. Here it turns out that if you actually calculate the Lyapunov exponent at fixed kicking strength as a function of this non-Hermitian parameter lambda, there is a place where the Lyapunov exponent seems to peak, and so yeah, so there is this peak in the Lyapunov exponent, and it turns out that this peak has something to do with a phase transition which this system has, which the Hermitian system does not have, and that phase transition has something to do with the breaking of what was called PT symmetry. So for those of you who might have been exposed to PT symmetric quantum mechanics, P being parity and T being time, it turns out that there are non-Hermitian systems which can have PT symmetry, and typically there is some parameter in the system which controls the amount of non-hermiticity, which in our case is this lambda. And so generally, actually generically for these PT symmetric non-Hermitian Hamiltonians, as you tune the value of this non-Hermitian parameter, you can have a transition from something called a PT symmetry broken phase, PT symmetry unbroken phase to a PT symmetry broken phase. And in this particular case, that transition seems to be also tied to the fact that the Lyapunov exponent in this system exhibits a maximum. So I will not be saying anything more about PT symmetric systems in this series of lectures, but if any of you is interested in discussing it, I'll be happy to talk to you offline. But this is just to show you another calculation of the Lyapunov exponent in a rather funny system, which is a non-Hermitian system. Okay, so fine. So that's all I had to tell you about the Kitt rotor. So the Kitt rotor is wonderful because, classically it's a very good illustration of a chaotic system with just 1 degree of freedom that's that's driven, and you can also get some semi-analytical results. For instance, for the Lyapunov exponent, quantum mechanically, the system is sort of reasonably simple to do calculations on numerically. However, there is one sort of essential feature of chaos which the Kitt rotor does not possess, simply because it has 1 degree of freedom. And that's a notion of a spreading of chaos in space as opposed to in time. So what we're going to do now is we're going to look at systems which are extended spatial systems, where you can actually look at the spreading of chaos in space as opposed to just divergence of trajectories, or in some sense the existence of chaos in time. So that's what we're going to do for the rest of the lecture. And so the specific systems that we're going to look at are the kinds of systems that we've already looked at, that you've already seen in my lectures and also other lectures in this school, which are spin systems. So we're going to look at one-dimensional spin systems and see what chaos means, quantum chaos means for those systems, especially from the point of view of the existence of a Lyapunov exponent and, say, the behavior of the OTOC. So that's what we're going to do next. So just to be concrete, so the kind of system that we're going to specifically study is some one-dimensional spin chain. So again, this same kind of system that we've looked at earlier. So you have a one-dimensional lattice of spins, and what I'm going to do to begin with is to assume that each one of these is a spin half degree of freedom. So these are all, again, this is just schematic, but these are all quantum spin halves. So 1D chain of quantum spin halves, and described by some Hamiltonian. And so what we're going to do is we're going to look at what the OTOC does for a system like this. And so again, the OTOC, and I shouldn't have erased that earlier, what I'd written earlier, is the expectation value of the square of this kind of commutator. And so you can ask, well, for this system, which is an extended system of spins, what would be appropriate choices for these operators W and V in order to investigate chaos in this system, right? So for the kicked rotor, for instance, because it had 1 degree of freedom, the simplest thing to do was to choose these to be the canonical variables. But what happens now? So, of course, it's quite obvious that whatever it is that we choose these to be, they have to be some combinations of the spin operators at every site. So each site has sigma x, sigma y, and a sigma z, and so w hat and v hat would have to be some combination of these spin operators in some way. And so the specific kind of combination that we're going to choose in order to look at the spatial spread of chaos is one in which w hat at time equal to 0, and of course v hat, in the OTOC in any case is only at time equal to 0. So the initial values of these operators are such that the commutator between them is equal to 0. Or in other words, what I mean by this is that you can think of w hat, for instance, as being some operator made up of the spin operators of these spins, which is centered at, let's say, this spin here, and then has a spatial extent which maybe goes from here to here. So let's say that is w hat. So it's made up only of spin operators in this particular region of the spin chain. And similarly, you can look at v hat, and v hat could be another such operator which is centered at this spin and is made up of spin operators within this region of the spin chain. And because these two regions are disjoint from each other, there's no overlap between them, the commutator of w hat and v hat is going to be equal to 0, because all the spins in this region, all the spin operators in this region commute with all the spin operators in that region. Of course, that is only what happens at time t equal to 0. But then as time progresses, when we are calculating the OTOC, this w hat is evolving. And what's going to happen is that if you have a Hamiltonian which basically involves terms which couple even just nearest neighbor spins, w hat is going to spread as a function of time. So it's no longer going to be confined to its initial region. It's actually going to spread out. And at some point of time, its spatial extent is going to be sufficiently large, right, that it's going to have like a sufficient weight in the region in which v hat exists. And that's when this commutator is going to start becoming sort of, non-zero, is going to start becoming appreciably large. And that's when the OTOC is also going to, in some sense, start becoming appreciably large. So that's sort of the qualitative picture. Now, one can actually go beyond this qualitative picture and make certain quantitative predictions and come up with certain quantitative bounds on how quickly this happens. And so, how?
This expectation values with respect to the initial state, or is it a thermal ensemble?
Okay, so I went over this the last time in the context of the kicked rotor. So with the kicked rotor, you could just, work with some wave, some initial state which is a wave packet, and just calculate the expectation value within that wave packet. Here, what you typically do for these calculations, at least the ones that I'll show, is one in which you're really doing some kind of infinite temperature calculation, where the state is just some unbiased average of all the states in the Hilbert space. Okay. So anyway, so coming back to what you can actually say about this, and I'll elaborate on this a bit more later in this lecture. But really what's happening is that this operator is now spreading because of its evolution due to just the usual unitary dynamics of the Hamiltonian. And so you can ask, well, how quickly does that happen? Is it a notion of speed? And it turns out, rather remarkably, that there is a notion of speed, and that in fact there is a notion of an upper bound for the speed, a maximum speed with which any sort of operator of this sort, or any commutator of this sort, can actually increase as a function of time. And so there's a bound that's called the Lieb-Robinson bound, And I think the Lieb-Robinson bound has been mentioned in previous lectures, especially in Michael Kastner's lectures. And so I'm not going to write down what the Lieb-Robinson bound is, because that's not going to be very pertinent for what I have to say. And I think Kastner probably did write down some expression for the Lieb-Robinson bound. But what it tells you is that things like this, quantities like this, can in some sense at most increase only so fast as a function of time, that there is some sort of limiting velocity which tells you how fast these things can increase. And this is actually a fairly remarkable result, because if you think of limiting velocities in physics, right? So the ultimate limiting velocity in physics is the speed of light. And the fact that the speed of light is a limiting velocity comes really from relativistic considerations. If you just look at non-relativistic physics, regardless of whether it's quantum mechanical or classical, there is no such thing as a limiting velocity. So the limiting velocity comes from relativistic considerations. Now here, when you write down the Hamiltonians for these spin chains, there's really nothing relativistic about those Hamiltonians. Nevertheless, there is a limiting velocity which somehow emerges in this non-relativistic system, and that really has to do with the fact that there is a particular way in which this operator is evolving as a function of time, that the dynamics is this unitary dynamics, and the Hamiltonian which is giving you the unitary has short range terms. And so because of the existence of those short range terms, and we'll see this in a slightly more detailed way later in the lecture, there is a natural way in which things move in space linearly with time, so that there is a limiting velocity. Okay. Anyway, but the basic idea as far as the OTOC is concerned is that we're going to look at these kinds of operators. And so to be a little more specific, what we can do is we can think of W, the operator W, as having a form like this. So it's some product of these spin operators. So let me write down the expression and then I'll tell you I plus BI K equal to J minus AJ to J plus BJ sigma hat K alpha K. Okay, so this is just a fancy way of saying that your operator W hat is something which is centered about site I, so center whatever, like its location is labeled by site I, and it goes from a distance AI to the left to BI to the right. So it's labeled by I, and it's confined to within a region which is of length AI plus BI, AI to the left, BI to the right. And the operator itself is basically some product, some arbitrary product of the spin operators which exist in this region. So that's what this multiplication here is. And these are just, so the K and also K here labels the sites, alpha K labels some particular component of the spin operator at the Kth site. And so this is some arbitrary combination like that. And similarly, V hat is another such arbitrary combination of spin operators labeled by the site index J, and within a range AJ plus BJ about J, AJ to the left and BJ to the right. So, yeah.
What was the reason behind choosing W and V to be commuting?
Sorry?
What was the reason behind choosing the operators W and V
Right.
to 0 at the initial time?
So what was the reason for them to have a zero commutator? Okay. So the reason for them to have a 0 commutator at time t equal to 0 is that then you know that at time t equal to 0, this particular quantity is 0, right? So if you want to see how, in some sense, the information is spreading from, right, so if in some sense you want to see how information is spreading as encoded by the OTOC, then you start with a situation in which this is equal to 0 and then subsequently increases. So that's what you're doing.
So, Subroto, I have two questions. So, one is that in practice, do you actually use single spin operators, or is it better to use these multi-spin?
Well, okay. So in practice, for everything that I think I'm going to show you numerically, it is single spin operators that you use. But the reason that you can write, but the point is that the general formalism, and I'll show you, what I mean by the general formalism in just a little bit, is something which also accommodates multi-spin operators. Right.
And I had a second question. So this OTOC, does it give you some extra information compared to, say, I measured something like a mutual information, which is again 0 as long as things are not entangled?
Well, okay. So I don't know if the mutual information can actually give you anything like a Lyapunov exponent. So that I don't think it can. Right. So really the thing is, so the difference between the OTOC and mutual information is, at the end of the day, the OTOC is in some sense really giving you classical information. I mean, it's giving you, for instance, in this case, a Lyapunov exponent, which is a perfectly well-defined quantity even in the classical limit. So the OTOC is really a way in which you are extracting some kind of classical information in this quantum system by looking at whatever would be the most appropriate quantum object which would give you that classical information, whereas mutual information is going to give you, this, I guess, complete quantum information for the system. So that's really more, in some sense, like the entanglement rather than this. Okay, and you can also presumably see that from the fact that the mutual information is really a property of the state and not so much a property of the operators, just like the entanglement, whereas here it's crucial what operators you're using. Okay, fine. So that is what. Yeah, sorry. Yeah, go ahead. Yeah, so a little louder, please. Huh. Okay, so all right, so now you sort of, yeah, so I guess the mutual information, in the way that at least I know that it's defined, is something where you extract the, okay, so you subtract out the classical information, and then what is left, if that is non-zero, you interpret as being quantum information, and the standard way of defining the mutual information is that. Okay, so anyway, so this is the kind of W operator and V operator that that we're going to look at. And so one interesting thing about, and a very nice convenient thing about this kind of W operator and V operator is that not only are these, of course, obviously Hermitian operators, clearly, but they're also unitary operators. So this is something which, often when you're working with Pauli matrices, you don't immediately realize. But if you think about it for just a few seconds, you realize that the Pauli matrices are not just Hermitian, they're also unitary. And so any such product of these spin operators, each of which is a Pauli matrix, is also, in addition to being Hermitian, unitary. Okay? And so that actually greatly simplifies things as far as the OTOC is concerned, because when you write down the OTOC this way, right, as the expectation value of the square of a commutator, and you open up the commutator, there are going to be 4 terms, because the commutator itself has 2 terms, and then you square it, and you get 4 terms. And mind you, these are operators, and so you can't just interchange terms and sort of club them together, because things don't necessarily commute with each other. But it turns out that if you also have, so in addition to the property that these operators are Hermitian if you also have the property, like those do, that these are unitary then that expression simplifies even further. So let me just write down what it simplifies to, and as an exercise you can do the algebra and convince yourselves that this is indeed true. So then C of t, which is the OTOC, which is this quantity now, given that the operators are also unitary, ends up having the following form. So 1 minus real part of f of t, where f of t is the following object. Okay, so f of t is just the expectation value of just one combination of these four operators, as opposed to if you'd open this thing out and you would have got four such terms. But it just turns out that because of the unitary nature here, two of those terms just give you one, and the other two terms combine to give you the real part of this object. And so this is convenient because in certain situations, it is actually much easier to calculate this than it would have been to sort of calculate that in a general sense. Okay, now the slightly unfortunate thing in the literature is that this quantity, f of t, is also sometimes called the OTOC. And so when you're reading a paper on this thing, on OTOCs, you have to be careful about whether the name OTOC is being used to refer to the commutator squared that I've written above, or whether it's being used to refer to this. So this is a slightly confusing thing. All right. Okay. So this is something which you can, in principle, calculate for these spin chains, and in fact that's what's done. But let's now look at a little bit. Let's look at what one would normally expect in terms of how this, how the OTOC actually spreads. And so first of all, what do we mean by the spreading of the OTOC? So what we mean by the spreading of the OTOC is what I had told you earlier, which is that you start out with a W and a V which commute at time t equal to 0, and then as time progresses, the commutator becomes non-zero. And so if you're looking at the OTOC, which is either that or this, it doesn't matter which one, which way you define it now, or which of these quantities you're looking at now, because they're equivalent, they're just related to each other in a simple way, then that is going to become non-zero as a function of time because W of t is spreading. So just for concreteness now, let's think of a Hamiltonian, a very general kind of Hamiltonian made up from these operators. So it's something of this form: I, alpha I, beta I, j I, alpha I. So let me write this down and then I'll tell you exactly what sort of system this describes. Okay, so this is just a very generic Hamiltonian for these spin halves on a 1D lattice. And I'm assuming, I mean, even though it's generic, I'm assuming just for this case, just for the sake of simplicity, that the coupling between spins is only restricted to being nearest neighbor. But beyond that, there is no other restriction. The coupling could be spin rotation symmetric like in a Heisenberg model, or it could have, say, some easy plane symmetry or some easy axis symmetry like in an XXZ kind of model, or it could have nothing. It could have, just completely different couplings for X and for Y and for Z, or the X of one could be coupled to the Y of the other, and so you could also think of, in some sense, spin orbit coupling. So all of those possibilities are admitted by having a term like this for the coupling. And then on top of that, there's also the possibility of having a magnetic field at every site, which couples to the spin at that site. So imagine that you have some very generic kind of Hamiltonian like this, and then you have defined operators W hat and T hat, like I had shown you earlier, so which are initially confined to separate regions of the lattice, and then W hat evolves as a function of time. So how exactly does that evolution of W hat take place, and what does that tell us about how this quantity, the O torque, changes as a function of time? Okay, so we know that W hat of t is just going to be e to the I h hat t by h bar W hat of 0. So that's what this is going to be. So one can actually write this by, so you can expand the exponential on this side and this side, combine terms, and then write down W hat as an infinite sum over these operators, and that particular infinite sum has this form. Okay, so it's basically going to be a sum where each term in the sum has some sort of nested commutator in it. So if we write this out more explicitly, then you can see that the k equal to 0 term, of course, is just the identity. So k equal to 0, sorry, it's not just the identity. K equal to 0 is just W hat. So the k equal to 0 term is just going to give you W hat. The k equal to 1 term here is going to be IT by H bar times the commutator of the Hamiltonian and W hat. And if you look at the k equal to 2 term, that's going to be IT by H bar whole squared by times 1 by 2 times the commutator of the Hamiltonian with the commutator of the Hamiltonian of W. And so similarly, if you look at the k equal to 3 term, aside from this prefactor, which will now have a different power of time, it will now go as t cubed, you're going to have the commutator of h hat with the commutator of h hat with the commutator of h hat comma W hat. And so as you go to higher and higher order terms, you're going to have nested commutators which are of higher order. So this is actually nice because in some way you write down W hat as a function of t in this way, you can actually see how the spreading is taking place by looking at higher and higher order terms in this commutator. And so the way to do that is, imagine that you've got that Hamiltonian, and just for concreteness, suppose W hat, as Arnaud was saying, is an operator which is restricted to a single site. So let's say W hat is one of the Pauli matrices at some particular site. So now what's going to happen? So the k equal to 0 term is of course w hat itself. So this operator is just going to be that, the operator at that particular site. Now if you look at what the k equal to 1 term does. So w hat is an operator which is confined to one particular site of this lattice, but h hat is something which has got nearest neighbor terms. And so when you take the commutator of h hat and w hat, h hat has a range which is nearest neighbor, w hat has a range which is strictly on site, and when you take a commutator of two such objects, what you end up getting is now something which is going to be of length nearest neighbor, right? And so this is strictly on site, this is going to be nearest neighbor, and then when you're calculating the k equal to 2 term, you're looking at the commutator of the Hamiltonian with something which is nearest neighbor. The Hamiltonian itself is nearest neighbor, and so when you're looking at these two, the commutators of these two, the outcome of that is going to be something which will have range which is next nearest neighbor, and so on. So as you go to higher and higher order terms, you can see that the range of w is increasing, and actually increasing in a linear fashion. So it goes from being strictly on site to nearest neighbor to next nearest neighbor to then third nearest neighbor and so on. And and of course, as that happens, so that's the structure of the nested commutators. But remember that the nested commutators in this expression are also accompanied by these prefactors which have time in them. Okay? So if you're looking at very short times, then of course the dominant term here, the dominant term is of course always going to be the k equal to 0 term, but then the next dominant term at very short times is just going to be the linear term. I mean, the other terms are going to be highly subdominant, and so at very short times you're just going to see the effect of the linear term, and then when you go to slightly longer times, then you start seeing the effect of the quadratic term, right? Because the other terms are still rather small and very, very subdominant. And so what's going to happen is that as time progresses, you're going to start seeing the effect of higher and higher order terms in this expansion. And when I say the effect of, I mean higher and higher order terms in this expansion contributing to the commutator, right, and contributing to the OTOC. And so because these higher order nested commutators are increasing the range of the operator in a linear fashion, and they're also accompanied by the corresponding power of t, you can see at least heuristically from this that what's going to happen is that the operator is going to spread linearly in time. And so just to schematically represent that, so here's time, and here is, let's say, something like the okay, I'm just going to call it w hat here. So this is just a schematic representation. This is the operator and this is time. At time t equal to 0, let's say the operator is just confined to one particular site, or rather, you can think of the x-axis here as being the lattice itself. So these are sort of the points on the lattice. At time t equal to 0, the operator is just confined to this particular lattice point, and then as time progresses, it's going to spread out linearly. And if you look at the operator v hat, the operator v hat, of course, is something which in the calculation of the OTOC is not changing as a function of time. We're just using the 0 time value of the operator v hat. So that continues to sit, let's say, at this point here. And so at some point, this linearly spreading front at some time is going to reach v hat, and that is when you're going to start, roughly speaking, you're going to start seeing some significant sort of value of the OTOC. Now, while all this is true, it turns out that this last statement that I told you is not really correct, in the sense that if that was sort of literally true, then you would say, you would think in some sense that when you calculate the O torque, there is a natural time scale associated with this O torque, which is the time scale over which you have the spreading of W hat to the location of V hat. And so if there is such a time scale, you might think that the O torque would sort of, increase in some exponential fashion with that time scale or something like that, but it turns out that that doesn't really happen. So, so what you can do is, you can actually show, just from this simple argument, that the O torque at some time t, so the O torque that I've written down, so let me write down the expression for the O torque again. So C of t is minus right? And so this object, just from this kind of argument, you can show is actually going to go as t to the L by L factorial squared, right, okay. So if L here is the distance between W hat 0 and V hat 0. So remember that what we assumed was that at time t equal to 0, these were separated in space. They were spatially separated, and each one of these was labeled by a certain site index, I and j. And so if L is the distance between I and j, if L is the spatial separation between these operators at time t equal to 0, then you can actually just sort of argue from this, from everything that we just discussed, that the O torque as a function of time is going to do this. So it's going to go as t to the L by L factorial whole square, which is really just reflective of the fact that, so this factor that we have here is just this p factor, the t to the k by k factorial that's sitting in the expansion, and then it gets squared because of the fact that the O torque, in the O torque finally you're squaring the commutator. So if you just go through with this argument, you'll see that that's the way you would expect the O torque to behave as a function of time for this kind of system. And so if you start with your W and V being sort of these very local operators and you calculate this O torque, you'll see that there is no exponential increase with time, and there is no Lyapunov exponent that you can actually extract. And so all of this, of course, as I said, was not a rigorous calculation. So you might say that, well, maybe there's some prefactors that you're missing, or if you sit down and actually do a rigorous calculation, writing down the sum properly, calculating the correlators, then maybe something would go wrong with this argument. But it turns out that that's not true. So let me show you some numerical data here. So this is the O torque for this particular spin chain. So this is just the Heisenberg spin chain. So you just have a Heisenberg interaction, and then you also have some on-site magnetic field, which I think here in this particular paper is drawn from some random distribution with a certain width. So it's definitely something which falls in this particular, it's a member of this particular family of Hamiltonians that I wrote. And so what you see here is you have a plot of the O torque as a function of time for two different operators W and V, which are initially separated by distances L equal to 1, L equal to 2, and L equal to 3. And you also have, and the calculation has been done for various values of H. And sure enough, what you can see is, you can see that there is actually there isn't an exponential increase. There is actually an increase which is a power law. And the power law does seem to have this form. So you can see the power law here goes as t to the power of 2L. And so when the separation is equal to 1, it's t squared. And when the separation is equal to 2, it's t to the 4th. When the separation is equal to 3, it's t to the 6th, and so on. So that's what you see. You don't actually see a region of exponential increase. So you have this power law increase, and then eventually, you have some saturation governed by some notion of an Ehrenfest time here. But there is no Lyapunov exponent that you can pull out. And so if you think about it, that's not surprising. And the reason that that's not surprising is that even for the kicked rotor, and just generally we argued that you can pull out a Lyapunov exponent when you have a meaningful semi-classical limit, when there is something in the problem that you can send to 0 in order to actually make the problem classical. Here, on the other hand, there is no such parameter. So if I take a spin chain of spin half objects, there isn't anything there really that I can set to 0 or infinity or something, so that I can think of the system as being classical, right? So this goes back to the fact that spin half objects, in some sense, are the most quantum mechanical spins that you can think of. So things actually do start becoming more and more classical as the spins in question become larger. So if you go from spin half to spin 1 to 3 halves and so on, and you keep increasing the spin, then the system becomes more and more classical. By the way, does anyone know why that happens? Why is it that as you increase the s of spin s, the system becomes more and more classical? I mean, there are many different ways in which you can answer this question, but can anyone provide me with one answer to this? Anyone?
If you talk about infinite spin, now your spin, if you think classically, has all the direction possible, so that it
Right.
can have all.
So basically the discreteness of the allowed, so if you look at, say, any particular component of the spin, let's say Sz, and you ask what are the allowed values of Sz, and so for any finite s, of course, the allowed values are discrete. You know that the allowed values are from minus s to plus s in steps of 1. And so if you look at delta Sz, the separation between allowed values of Sz, that is equal to 1, regardless of what s is. But if you look at delta Sz relative to the size of s, right, this is going to go as 1 over s. And so as you take s to infinity, this separation between allowed values of spin relative to the size of the spin is going to go to 0. And so this becomes more and more classical. Another way of seeing this is if you look at the commutator between spin operators. So if you look at S alpha hat, S beta hat is equal to I h bar epsilon alpha beta gamma S gamma, and you factor out the magnitude of the spin from the spin operators, so that in some sense the operators now have operator norm 1, okay? So then what you're going to get is you're going to get a factor of s on the right hand side, you're going to get a factor of s squared on the left hand side, and so what you have effectively is a factor of 1 over s on the left hand side. And so as s goes to infinity, the commutator goes to 0, and that is again like a classical situation. So given all of this, you would then expect perhaps that a classical limit or a semi-classical limit in which you could extract a Lyapunov exponent, even for a spin system, is one in which you go beyond these spins being 1/2 and actually look at higher spins. So let me show you a calculation here of exactly that. So I should have labeled this diagram a little better. But so what these people have done is they've actually looked at a spin J Hamiltonian. So you have this particular kind, so this is again very much within this class of Hamiltonians that I wrote down, except that now these spins are not spin half, there's some higher spin. And for reasons of calculational simplicity, they chose to work with this as opposed to, say, a Heisenberg Hamiltonian. I'm guessing that had they worked with a Heisenberg Hamiltonian, the results wouldn't have been qualitatively any different. But so this is what the Hamiltonian is, and as you increase J, it becomes more and more classical. Yeah. Sorry, yeah.
Is there any way to see from this BCH argument that when this S becomes large, this growth is going to be exponential?
So the H bar here is
From the BCH argument here, is there any way to see that if I increase my S, this power law growth is going to be exponential?
no. Okay, so I don't think there is. Not that I can easily think. I mean, okay. So what would happen presumably is that. So when you write down these nested commutators now, so okay, so let me just back up. So notice that in this Hamiltonian, the way that they've written it is they've taken out this factor of square root of j times j plus 1, which is like the overall magnitude of s because they have some quadratic term, right? So now if you're going to use this argument for a general spin s, once again it's probably best to write down the Hamiltonian with this thing factored out, and then probably what happens is that, let's see, if you do that, of course you're going to get larger and larger, right, so what will happen is that in these, I'm just, as the Americans say, spitballing here because I haven't thought about this very carefully, but my guess is what will happen is that when you pull out this factor of s times s plus 1 and you send that to infinity or you make it very large, then you see that all these different terms in the w hat are now going to be, reasonably large. Each one of them is going to be, like the time is not going to suppress it because of the fact that, okay, so the reason that this thing is spreading is that if you're looking at a small time, a short time, right, this factor is going to suppress the corresponding term in the expansion. But then if you also have some other factor in h, which is large, to counterbalance that suppression, which is this s, with exactly the same power, then it's not going to happen that at short times it's only going to be the lowest order term which will be dominant and the other terms will be subdominant, because the subdominance of the other term now will be compensated by these additional factors of s. So in some heuristic way like that, you can see that it's no longer going to be power law, that it can actually end up being exponential. But as I said, this is just me spitballing. This is not an exact calculation of any sort, but this is just some general sort of hand-waving, very, very vigorous hand-waving argument, which would tell you that you can go beyond having a power law growth.
It's not completely obvious from there, because if I just naively think about your argument, it seems to me that I can absorb those powers of s and define a rescale time, and then everything remains the same.
A rescale time, sorry?
Yeah.
No, but right. So, yeah. Okay, so imagine that you do that. You absorb those powers of s into the time itself, and you define a t star. But then your t star is going to be s times t, and then when you take s to infinity.
Maybe that's the answer. Yeah. Okay. Yeah.
Right.
So that regime just shrinks.
Right.
Yeah.
So presumably that's what happens. But one needs to sit down and actually do the expansion properly. But if you look at this thing numerically, so that's what these guys have done here. So there is, you pull out this factor of j because that sort of defines for you an overall scale. And so what's in these plots is basically j into j plus 1 times the O top as a function of time, and each one of these is for a different value of j. That's the thing which I should have indicated on this slide, which I didn't. And so this blue curve here is for the smallest value of j, the one that's here, which is j equal to 1/2, and then this is j equal to I think 1, and then they basically keep increasing the value of j. And you can see that as the value of j increases, there is actually something like an exponential region which seems to emerge. So aside from what is happening initially, which is j independent, beyond a certain time scale, you can actually see that for at least the largest values of j on this plot, where you have, this is a semi-log plot, there is a straight region with something which looks like some kind of Ehrenfest saturation. And so this demonstrates that as you increase the value of the spin, the magnitude of the spin, you can actually start now accessing an exponential region and actually pull out a Lyapunov exponent. And this is the way you can get to a semi-classical limit for a spin chain. But there is really no semi-classical limit for a spin half spin chain or a spin one spin chain. And in fact, just as a, sorry, okay, using this, not that.
So just a quick question. If you go back to the last talk, as you said, there's an early time regime where the result is sort of J independent. There, is it like a power law, just like the SE?
I don't, I mean, you can look at this here, right? It certainly, it doesn't look like, well,
Yeah, because this
I mean, it could, yeah.
Yeah, this naive T star argument would tell you that there should be an early time power law somewhere, but maybe it's
Right,
so short that
right,
it's not
right.
fitting.
It probably is like here, yeah, I mean this, yeah, all of this should really, I guess, it's probably just the power law here. And the reason that you can see that it's probably that power law is that this argument, the way that the O torque increases as a function of time, is independent of what spin S you choose. It's just going to go as t to the 2L, regardless of whether it's spin half or spin one or some other spin. And it's probably just that. And then you see the divergence once the other, if as time progresses, and for larger S, the other terms kick in. Okay, so fine. So the one thing which I should just mention, and this is very much, as far as I know, still not a settled issue, is that, so what I told you from the, or what I sort of argued from the conclusions of this paper was that for spin half at least you don't see this exponential, you just see the power law, and there's no way in which you can pull out a Lyapunov exponent. But in the interest of completeness, and I should tell you that there are people who argue otherwise, saying that while you can't really pull out a Lyapunov exponent from this part of the plot within this sort of region of time, there is actually a Lyapunov exponent that's hidden here. So, so what I'll do is I'll just mention, maybe just tell you what the relevant reference is and tell you what the particular functional form is that's been argued to hold and where the Lyapunov exponent comes in, and just leave it at that. So there is an argument that's been presented backed up by numerics on spin systems like this, but more accurate numerics than the ones in this paper. So the numerics in this paper are, so these are exact diagonalization numerics, but you can do something a little more sophisticated. You can do numerics based on what are called matrix product states, MPSs, which I won't go into. The only thing that you need to know is that in some sense that's more sophisticated than just exact diagonalization numerics. But so there is this conjecture by Xu and Swingle, and this is from 2020. I don't seem to have the exact reference in my notes here, but I will put the reference up on a slide and then give it to the organizers. But this is, I think, Nature Physics from 2020, where they propose the following form for the O torque after the power law growth has been saturated. So basically something that applies to this region here, where they say that the O torque has the following form. So let me just write this down and I'll tell you exactly what this is. Exponential of minus lambda x by v minus t Okay, so x here is the distance between the operators w and v. So it's the thing which I've been calling L, no, this, so in this notation it's x. And so the conjecture is that beyond this linear growth, when you go to that region where it looks like the OTOC is sort of oscillating, saturating, you can, in some region of about a decade or so in time, try to fit this form to the OTOC with this parameter p, which they further argue for a spin half chain p is equal to 1/2, but it's also not true that for a spin s chain p is equal to s. That was not true. It just turns out that for s equal to 1/2, p is equal to 1/2. So it has this form. And so now you can see two things here. So one thing which you can see is that there is a v here which is like a velocity. So this OTOC is, there is an implicit velocity in here. There is ballistic propagation in this form of the OTOC. And the other thing is a lambda sitting here, which is what they interpret as a Lyapunov exponent. Even for a spin half system, but one which somehow presents itself not in at this early time increase of the OTOC, but rather at later times when, if you look at the OTOC on a plot like this over this kind of sort of range of times, it will look like the OTOC is saturated, but it's actually not saturated. There is about a decade or so in there where you can fit, yeah. Sorry? Yeah.
Is it just a ballistic propagation because there is a t to the power of p sitting on the denominator? So probably there will be some creativity.
No, so it is ballistic because of the fact that, because of the presence of this factor. Yeah, but you're talking about the t to the p down here. Yeah. So okay. So in general, when p, even in something like the Lieb-Robinson bound, for instance, you are allowed to have these factors of t. So in fact, since in the remaining 10 minutes or so that I have, I'll show you something else for a completely classical system in which, again, you're going to have a form which is similar to this, but with a different power of p. So basically, the ballistic nature really comes from saying that you have a factor of x minus vt. That is, and there's a velocity that you can define there.
So basically, there's a front.
Front is propagating ballistically. Right.
But Subroto, one quick question. In this particular paper that you mentioned, do they give any interpretation of this Lyapunov exponent in terms of any transport coefficient?
In terms of transport coefficients, no. No.
Does such an interpretation exist, or do people believe that it can exist?
Well, I would think not, and the reason for that is that you can. Okay, so if you look at this model and suppose there was no h, then of course this is just the quantum Heisenberg model, nearest neighbor quantum Heisenberg model, which is integrable. And so if you were to look at transport in this system, then the transport would be ballistic, right? Nevertheless, I think even without the hi, and you can probably see that even from their plots here, even for h equal to 0, actually I don't know where the h equal to 0 is, but what I was trying to, okay, here in any case there is no Lyapunov exponent, or the one that you get from here. All right, fine. The one that you get from there is a Lyapunov exponent. And so you'll get some Lyapunov exponent for h equal to 0 as well. And the transport is ballistic. Now you could maybe add some next nearest neighbor interaction, break the integrability so that the transport is now diffusive. And even in that case, presumably, and I'm saying this presumably because I don't know if the calculation has been done, there's going to be a Lyapunov exponent. So you can see that regardless, if this is indeed true, regardless of whether the transport is ballistic or diffusive, you have a Lyapunov exponent. And so then there's no simple way of connecting the Lyapunov exponent to a transport coefficient, at least that I know of. Okay, so I thought I'd just mention this to you. For those of you who are interested, you can actually look at the paper and see what the arguments are which underlie this particular conjecture. So in the remaining 5 minutes or so, let me just show you something about some data for just two kinds of classical systems in which you can you can actually numerically calculate the O torque. You can, and then these are completely classical systems, and you can actually see a ballistic spreading of the O torque. So since I've, in this context, defined C of x comma t, so this is now the O torque at time t for two operators which are separated by a distance x, okay? So you can now actually define something like this even for a classical system. The only thing is that for a classical system, you might wonder what it means to talk about two operators that are separated by a distance x. So for the classical systems that, for which I'll be very briefly discussing, the idea now is the following. So we just go back to thinking in terms of classical chaos. So forget about all the stuff that I told you about operators for a quantum mechanical system. Just go back to thinking about a classical system and sensitivity to initial conditions. But the classical system in question now is a classical spin chain. So exactly the same thing that we were looking at in a quantum mechanical context. Imagine that you now have a classical spin chain. So you have three-dimensional rotors on a one-dimensional lattice. So at each point on this one-dimensional lattice, you have a classical rotor which has some spin s or whatever, some length s or something. And this system is just described by the classical Heisenberg model. So J summation over J Si dot Si plus 1. These are not operators. These are now just classical spins like we considered in the first lecture, but now you have a whole lattice of these. And now what you can do is you can start the system out with some particular initial condition, let it evolve, start the system out with some other initial condition, let it evolve, and then just look at the divergence of these trajectories. But there's a way in which you can look at the divergence of these trajectories for the classical system in a way which is equivalent to calculating the O torque. So I won't really go into that, exactly what that is. But the point is that these two initial conditions that I'm going to choose will be identical everywhere except at one particular spin. So it's only going to be one particular spin which will have a different value for these two initial conditions. All the other spins will have the same value. And these two initial conditions are going to be only slightly different from each other. And so then you can ask how this difference in the spin is going to propagate as time increases. And so that's what I have here on this plot. So this is basically just the classical Heisenberg model, right, which has that Hamiltonian and this equation of motion. And you start the system out with two different initial conditions, which are different only at the for one particular spin which is located at x equal to 0. And then you go ahead and calculate this O torque. You can think of it now actually you can think of it in terms of Poisson brackets like we described earlier instead of commutators. Just go ahead and calculate that. And you calculate it over an ensemble of such pairs of initial conditions, an unbiased ensemble of such pairs of initial conditions, all of which differ only at the site x equal to 0. And you can see that this has a nice ballistic form. It has a nice ballistically propagating front. The red region is where the O torque is large, and the blue region is where the O torque is small. And across this front, you actually have a form of the O torque. So here, in this particular paper, they've used the symbol D instead of C for the O torque. It's the same thing. So across this front, you have this particular form for the O torque, and the alpha here is like a Lyapunov exponent. So you can pull out a Lyapunov exponent for the spin system. And then you also see that there's a velocity here, which is this velocity of propagation, also called a butterfly velocity. And this is pure for this completely classical system. You get this Lyapunov exponent and this velocity. So the very last slide that I'm going to show you and end is again, something that I've done with some collaborators. So this is again exactly the same classical system, classical three-dimensional rotors on a one-dimensional lattice, except that the dynamics is a little strange. So unlike the Heisenberg model, where if you were to write down the dynamical equation, this is what you have. This is also what we'd written down earlier in for one of our lectures. So there's Si cross Si plus 1 plus Si minus 1. So Si plus 1 plus Si minus 1 is like the effective field at that particular point. And so Si basically feels a torque due to that field. And so this is the dynamics for the Heisenberg model. So what we have here is, instead of Si plus 1 plus Si minus 1, we have Si plus 1 minus Si minus 1. Now you might wonder why you would even look at a model like this. So this model is actually in a general class of models which are called non-reciprocal models. And I'm by no means an expert on this, but in classical StatMech, these kinds of models are important, especially in the context of what's called active matter and active systems, where you assume that you have some system with some degrees of freedom, which by themselves, when they interact, would have some nice Hamiltonian description with some reciprocal interactions. But then if there's a particular kind of drive that is given to these systems, there's a particular way in which you can pump energy into these systems, you can end up with effective dynamics which is non-reciprocal. So here, the funny thing about this kind of dynamics is that unlike in the Heisenberg case, where the torque exerted on spin I by spin I plus 1 is equal and opposite to the torque exerted on spin I plus 1 by spin I, in this funny model, the torque exerted on spin I by spin I plus 1 is equal to the torque exerted by I plus 1 on spin I. And so it's not equal and opposite. As a result, as opposed to the Heisenberg model, in this model, the total spin is not conserved. The total magnetization is not conserved. It actually turns out that it's the total staggered magnetization which is conserved. And there's also no Hamiltonian from which you can derive this dynamics using the usual Poisson bracket relations between the spins. So this is, in that sense, a manifestly non-Hamiltonian system. Physics is specified completely by its dynamics and not by a Hamiltonian from which you can get the dynamics using the Poisson bracket between spins. Nevertheless, even in this system, you actually can, in exactly the same way as for the Heisenberg model, have a spread of the O torque, define a Lyapunov exponent, get a velocity of spreading, get a butterfly velocity, and in almost every respect, it is like the Heisenberg model, right? Except for the fact, of course, that the value of the Lyapunov exponent that you get and the value of the velocity that you get is different. But qualitatively and even quantitatively, in terms of the form of the O torque and the way that this disturbance is spreading, it's exactly like the Heisenberg model. And so the notion of an O torque, this kind of O torque, is not, first of all, is fairly general. It's not something which you use only to characterize Hamiltonian systems. You can also use it to meaningfully characterize non-Hamiltonian systems like this, extract the Lyapunov exponent and a butterfly velocity. And indeed, there are other similarities between this non-reciprocal model and the Heisenberg model, which I won't go into. It turns out that even this model displays, has diffusion, has conserved quantities, has diffusion, has a certain notion of thermalization, etc. But that's not, the thing that I want to emphasize. So I'll just end with this. And so hopefully I've been able to impress upon you the importance of the O torque, how it generalizes the notion of the spread of trajectories from a classical system to a quantum system. It allows you to calculate Lyapunov exponents, gives you yet another way to characterize quantum chaos, in addition to the ways that Lea Santos and even Orno told you about, level spacing statistics and looking at the eigenstate thermalization hypothesis and so on. This is yet another way to do it. And okay, so I'll end this lecture here. I have 2 lectures left. So in the next lecture, I'm actually going to talk about the eigenstate thermalization hypothesis and tell you how the eigenstate thermalization hypothesis basically, in some sense, arises out of looking at random matrices, and how if you had a Hamiltonian which was a random matrix, then there's in some sense a reasonably simple way for it to thermalize, for it to reach thermal equilibrium. And that notion can then be extended to more general systems which are not really random matrices, but are described by the eigenstate thermalization hypothesis, how that approach to thermalization happens. So that's what I'm going to do in my next lecture. And in my final lecture, I'll tell you a little bit about open quantum systems, and in particular what the quantum master equation is, something called the Lindblad equation is, and how one looks at open quantum systems within that paradigm. Okay, thank you.